Okay, let us discuss this problem. This is a quite good problem discussing something about resonance energy. So this says biphenyls has the following structure. So structures of biphenyl is given to you. So this is the structure of a biphenyl. Now question says, first part of the question is biphenyl is a fused aromatic hydrocarbon. So question is asking whether this is a fused or not. So does this biphenyl is a fused hydrocarbon? Are you getting? So is this fused or not? Now the definition for fused says any two ring if two atoms are common. So you have a two ring and two atoms are common, generally carbon atoms, then system is called fused system. So ring must share two atoms to be called fused. So this is not a fused system. So this is not a fused system because it does not contain two atoms that is shared. So to be fused, I can say two atoms should be shared. And in this case, two carbon atom generally. Two carbon. If you have nitrogen is there, that is also true. Two carbon atom in this case is carbon atom, generally carbon atom. Two carbon atoms should be shared. At least. Of course, you can have two carbon atom one sided, two carbon atom other sided, that will be shared. That is again a case of fused system. Now B part of the question says, so this is example of fused system. So this system is a fused system. In this case you have two carbon, this carbon is basically in sharing with this ring and this ring. So this carbon is in the sharing with this ring and this carbon is also in the sharing with the two rings. So carbon, these two carbon are part of these two rings. So that's why this is a fused. This molecule is basically naphthalene. You can have another example of this. Something like that is called anthracene. This is also a fused system. Are you getting? Let us discuss B part of the question. So B part says, how many pi electrons are there in two aromatic rings of biphenyl? So how many pi electron we have in biphenyl? So this is an example of biphenyl. And the now question is asking how many pi electron we have. So we have 2 plus 2 4 plus 2 6 and 6 this side. So we will have total 12 pi electron. So this system contains 12 pi electron. How does this number compare with naphthalene? So if you see naphthalene, so how many pi electron you have in case of naphthalene? So this molecule is naphthalene. So you see 3 and 2 5. So you have 10 pi electron in case of naphthalene. So there are 2 more pi electron in case of biphenyl compared to naphthalene. Now part C says the heat of hydrogenation of biphenyl is around 100 kilocalorie per mole. So heat of hydrogenation, delta H for hydrogenation, and hydrogenation means I have biphenyl, this is a biphenyl, and if I add hydrogen, so how many mole of hydrogen I have to add? So 12 pi electron, so I have to add 6 mole of hydrogen. And this will completely hydrogenates. And questioner says in this process the amount of heat that is released, that is given to you. So amount of heat released in this process is 100 kilocalorie per mole. So in this process amount of heat released, that is 100 kilocalorie per mole. So for 1 mole is 100 kilocalorie heat is released. Now we have to find what is the resonance energy. So we are interested in resonance energy of this molecule. And one more information is given to you. For an isolated alkene, for one double bond, if I have a one double bond, And if I do, so let us say hydrogen is here, and if I do hydrogenation, so if I add 1 mole of hydrogen, finally I will have CH3. So if you reduce 1 mole of double bond by 1 mole of hydrogen, the amount of heat liberated is 28.6 kilocalorie per mole. So in this case, delta H is 28.6 kilocalorie per mole. Are you getting? So calculate the resonance energy in this case. So how will you proceed? So you see, if you have 1 mole of double bond, if you reduced, the amount of heat liberated is 28.6. Now if you have 6 mole of double bond, 1, 2, 3, 4, 5, 6. So if you reduced 6 mole of double bond, so you will expect, so expected heat liberated should be, so this is the amount of heat liberated for 1 mole of double bond. So you have 6 mole of double bond, so you will have expected heat liberated, that is heat of hydrogenation. So expected heat of hydrogenation should be 6 into 28.6 kilocalorie. Are you getting or not? So this is the amount of heat one can expect if we have 1 mole of biphenyl. So this is per mole of biphenyl. So this value comes out to be 6 into 28.6. So let me do this one. So 6 into 28.6. This value 171.6. So let us say around 172. So this is comes out to 172 kilocalorie. Now, but the actual heat liberated is, you see in this problem this says actual heat liberated is only 100 kilocalorie per mole. So actual liberated is actual heat of hydrogenation, this is only 100 kilocalorie per mole. So this means the rest of energy that has been not liberated is basically goes to stabilize the molecule, and that is the resonance energy. So in this case I can say resonance energy is, RE for resonance energy will be 172 minus 100, that is around 72 kilocalorie per mole. So you see, biphenyls are having resonance energy of 72 kilocalorie per mole. If somebody asks what is the resonance energy of naphthalene per mole of double bond, so if you see there are 6 pi bonds, so per pi bond resonance energy, if I want to calculate per pi bond resonance energy, and in that case I have to divide this by 6, 72 by 6. So that is around 12 kilocalorie per mole. Are you getting or not? So this is per pi bond, this is the resonance energy you have. Are you getting? Now D part of the question says, so we have calculated the resonance energy. Now D part says, this says compare the resonance energy of biphenyl with that of naphthalene and with 2 benzene rings. So you have to calculate the resonance energy, compare the resonance energy of naphthalene, biphenyl with naphthalene first, and with 2 benzene ring. So let us first compare with 2 benzene ring. So this is a biphenyl, and in this case resonance energy we have already calculated, that is 72 kilocalorie per mole. Now if you have a benzene, for benzene resonance energy is 36 kilocalorie per mole. So now if I compare these two, so you see here are 2 benzene rings you have. So in naphthalene 2 benzene ring and the resonance energy is 72. So in naphthalene per benzene ring the resonance energy is 36, that is same as resonance energy of benzene. Are you getting? So in naphthalene I can say, in biphenyl, this is biphenyl. In biphenyl resonance energy per mole of benzene ring, because there are 2 mole of benzene ring, per mole of benzene ring, this is equals to 72 by 2, that is same as resonance energy of benzene, is same as, and that is same as, so you can write, that is same as the resonance energy of benzene. Now let us compare this with naphthalene. So naphthalene has the resonance energy, this you have to remember, or it should be given in the problem. So naphthalene has resonance energy of 60 kilocalorie per mole. So naphthalene has a resonance energy of 60 kilocalorie per mole. In the case of naphthalene also you have 2 benzene ring. So again in case of naphthalene I can say per mole of benzene ring. So in naphthalene resonance energy per mole of benzene ring this will be equals to 60 divided by 2, that is 30 kilocalorie per mole. But in case of biphenyl this is 36. Are you getting? So you can say per mole of benzene ring biphenyl has more resonance energy than naphthalene. So I can say biphenyl has more resonance energy. So resonance energy of biphenyl is greater than resonance energy of naphthalene. If you compare per mole of benzene ring, and this is obvious, it should be. And now if you see in case of naphthalene, how many pi electron we have? In case of naphthalene 6, 8, 10. So you have only 10 pi electron. But in case of biphenyl you have 12 pi electron. So there is more destabilization, more delocalization, and that will make the molecule more stable. Are you getting? But if you see in case of naphthalene, let us try to see in case of naphthalene what is the per double bond, what is the per double bond, what is the resonance energy. So how many double bond we have? 1, 2, 3, 4, 5. So per double, in case of naphthalene, per double bond energy is 6 kilocalorie per mole. So let us write this one. Per double bond, per pi bond, resonance energy in naphthalene, resonance energy in naphthalene. So let me write naphthalene. This will be equals to 30 by 5 because I have 5 pi electrons. So 30 by 5, that is 6 kilocalorie per mole. Why I am using this we will understand soon. So if you compare in terms of pi bond, in terms of 1 pi electron, both have same resonance energy. You see the resonance energy of biphenyl per double bond is 36 by 6, that is again 6 kilocalorie per mole. In case of naphthalene also 30 by 5, that is 6 kilocalorie per mole. So if you see in case of naphthalene and in case of biphenyl, both have same resonance energy in terms of per mole of double bond. That is important. We'll discuss the next problem.